Hi, I want to welcome you in to the fascinating study of biological anthropology. It is the story of us, and today we're going to be talking about bipedalism. Now, according to our textbook called Explorations, an open invitation to biological anthropology, early hominins like Australopithecus afarensis were already fully committed to bipedalism well over 3.6 million years ago. But if we include the discipline of biomechanics, it helps to explain why this matter, right? Walking on two legs, bipedal locomotion, it drastically and dramatically reduces energy use over long distances. In fact, comparative research and studies shows us that a chimpanzee walking upright uses 4 times more energy than a human walking the same distance. Our anatomy turned walking into an energy saving strategy. It was perfect for early hominins who traveled between scattered food patches and resources on the African landscape. So, some of the key skeletal features that makes bipedalism possible. Bipedalism is a tongue twister. It's about walking on two legs. What makes it possible is the foramen magnum. The foramen magnum, the hole where the spine enters the skull, is perfectly positioned underneath the head in humans. Now, this allows the skull to balance directly above our spine, reducing musculature effort while walking. Not only was the foramen magnum important, but also our S-shaped spines. Now, humans have a distinct S-shaped spine, which acts like a shock absorber. It keeps our center of gravity aligned over the hips, preventing us from tipping forward. Now, the next pivotal skeletal feature is a short, broad pelvis. Now, this is interesting. The human pelvis is shaped like a bowl. We learned this in class. This stabilizes the trunk during leg stance phase of walking. The moment one foot is off the ground, right? That's what the leg stance phase of walking is. It also requires an angled femur, or the valgus angle, right? Our femurs angle inward toward our knees, bringing our feet closer to the body's midline. The unique angle of our femurs minimizes side-to-side sway and increases walking efficiency. Then there's the arched feet and enlarged heel that humans have. We humans have longitudinal and transverse arches and a large heel bone for heel strikes when we walk. These structures store and release energy like springs with every step. Then again, there's another crucial feature called the gait cycle. What happens when you take a step? What's really intriguing to me about the gait cycle is that there are 2 phases, right? There's the stance phase. Now, the stance phase incorporates about 60% of walking. Then there's the heel strike. Your heel contacts the ground. Then there's mid stance. The body vaults over the planted leg. Then you have the toe off. The toes push off and store elastic energy in the foot arch. The second phase being the swing phase, which makes up the remaining 40% of bipedalism, right? The foot swings forward. The opposite leg prepares for the next heel strike. This rhythmic exchange creates the smooth, pendulum-like motion that makes human walking so efficient. Understanding how and why we walk not only deepens our grasp of human biology, it also connects us to the long lineage of hominids who walked millions of years before us. I hope you enjoyed this brief breakdown of how we became walkers, bipedalism. Thank you for tapping in with me. I hope you enjoyed this class as much as I did.